Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is lecture number 63 and this is also tutorial number 17. Now in the previous tutorial session, that is tutorial 16, which corresponded to lecture number 62, we were looking at the various aspects related to selection rules associated with rotational and vibrational transitions. In this tutorial, we shall start with selection rules concerning electronic transitions for atoms, and I will give you a brief hint as to how to connect the selection rules for atoms with those of molecules. Okay, so we shall proceed straight away into the tutorial. So the question for today is going to be, what are the selection rules for electronic transitions in atoms? All right, so this is what we shall be looking into today. And note that if time permits, by the end of this tutorial, or maybe some part of the next during some part of the next lecture, I should also be very briefly highlight the selection rules for electronic transitions in atom. So what I've written here is electronic transition in molecules. All right. Okay. So let's right away jump into the subject. So the answer for this question is that, recall that the selection rules for vibrational and rotational transitions, we express them in terms of what? We express them in terms of the rotational quantum number and vibrational quantum number, correct? The rotational quantum number came from the rigid rotor model, and the vibrational quantum number came from the harmonic oscillator model, and we also took some effort to consider anharmonic effects also, correct? Okay, so now let us see what the selection rules for the electronic transitions are going to be expressed in terms of. What would be your initial guess? Without knowing anything, what would you guess? Just based on the connection between your rotational and vibrational transitions with the electronic transitions. It has to be some quantum number, right? We don't know yet what quantum number it is going to be, okay? But it is going to be expressed in terms of some quantum number. Now, I will tell you that these quantum numbers are going to be the same quantum numbers that you started off whenever you started studying about electronic configurations in atoms, probably in your 11th or 12th standard, and perhaps even in college, okay, right? So the point I'm trying to convey to you is that to understand selection rules for electronic transitions in atoms, so for electronic transition in atoms, selection rules will be in terms of quantum numbers. Now, what are the quantum numbers that you are aware of? Well, the quantum numbers that you are aware of, from 11th and 12th standard, while discussing the electronic configuration of atoms, we're talking about the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin quantum number, right? So these are the same for quantum numbers. In fact, The principal quantum number itself might not play a big role, but the three other quantum numbers will play a very big role in determining the selection rules. Okay. Now, recall that from your 11th and 12th standard high school, and perhaps some introductory college. Okay, right? For every atom, we can write its electronic configuration. Right? So what will the electronic configuration be expressed in terms of? The three quantum numbers, principal quantum numbers L, the azimuthal quantum number L, the magnetic quantum number M sub L, and the spin quantum number S. And recall, in an earlier lecture, perhaps around lectures 45 or 46, when I was discussing about the transition moment integral, I was telling that these three quantum numbers arise from the wave function of a molecule, especially from the hydrogen atom, the solution to the hydrogen atom problem. And this quantum number arises separately. Nonetheless, all of these are important as far as the selection rules are concerned. In particular, these three quantum numbers, the L, M, and S, M sub L, and S, are going to be critical to understand selection rules in the electronic transitions for atoms. Okay. Now, before me, telling anything, what do you think these quantum numbers come up in the selection rules? Well, the answer to that is note quantum numbers arise in the selection rules as part of the dipole moment integral. Please look up earlier lectures, for example lectures 45 or 46, to understand what this is. I only gave a qualitative understanding, but by computing this, we shall be getting selection rules in terms of L, ML, and S. Although the exact mathematics I'm discarding for this course. Okay, please note this. All right. So, having understood that the quantum numbers are going to be part of the selection rules, let's see that. Let's take an example. Okay, take for example the electronic configuration of oxygen atom. What is going to be the electronic configuration of oxygen atom? Well, we know that it is 1s2, 2s2, 2p4, correct? This is the ground state electronic configuration of oxygen atom as we all study in school. So this is completely paired. I mean, both 1s2 and 2s2 are completely paired, and your 2p4 could be written as, let's say, just going by convention XYZ, right? Let's say 2px2, 2py1, and 2pz1, correct? So this is paired, and these are two unpaired electrons, the 2py1 and 2pz1, correct? And conventionally, because the p orbitals are degenerate, in the absence of any external magnetic field, we are also going to be writing the 2p4 electronic configuration as following the Hund's rule. You first fill your XYZ, and then you pair the electrons, correct? So this is going to be corresponding to M sub L equals +1, this is ML equals 0, and this is ML equals -1 by convention. Okay, right? I'm just going to call this as PX, PY, and PZ. Are we clear? Okay. In fact, this doesn't matter. Okay, it depends on the choice of our axes. Okay, but by convention, we first fill the M sub L equals +1, then go to 0, then go to -1. All right, yeah. Okay, now corresponding to this electronic configuration, of course, there are 4 quantum numbers involved here. All four quantum numbers are involved. The principal quantum number is involved in the sense that the 1, 2, the labels outside it. The azimuthal quantum number is also involved because we're talking about which quantum number, right? S corresponds to L equals 0, P corresponds to L equals 1, blah, blah, right? And of course, the magnetic quantum number, M sub L, is also involved here. And the spin quantum numbers are also at play. Are we clear, right? So now, we understand that the quantum numbers play a role in selection rules. But, this is a bit of a messy notation, right? If the electronic configuration involves, well, knowledge about all the shells, right? All the shells. Now, this can be written in a more shorthand notation, okay, right? Now, a more succinct notation for the electronic configuration, right, is what is called as a term symbol. And that shall be extremely useful in obtaining our selection rules. I'm now going to be introducing a new terminology called as the term symbol. It is that a more succinct or a more precise and shorthand notation for any given electronic configuration is what is called as a term symbol. And this term symbol, right, can be easily used in the specific selection rules. Specific selection rule. I'm just using the same abbreviation we've been using all along. Okay, right? So, for example, the electronic configuration of oxygen, that is 1s2, 2s2, 2p4, right, which corresponds to 1s2, 2s2 and 2px up and down, 2py up and 2pz up. See, by convention, we put the spin pairs to be both up. It can also be down, it doesn't change anything, but we're just following the convention and then we go with this particular one, okay, right? And arbitrarily assigning values of M sub L equals +1, M sub L equals 0 and M sub L equals -1. All right. So corresponding to this electronic configuration, we have what is called as a term symbol. Okay. Now, this term symbol is extremely critical in electronic spectroscopy. All right. So all our selection rules are going to be expressed in terms of the term symbols themselves. Let us see how. The electronic configuration can be written in terms of a term symbol, and for every given electronic configuration, I'm just going to write this as EC. Okay, electronic configuration. For every given electronic configuration, a term symbol can be uniquely associated. Okay, right? So for any given electronic configuration, a term symbol can be uniquely identified. Okay, a term symbol can be uniquely associated. For example, okay, this specific electronic configuration, not just 1s2, 2s2, 2p4, but this specific ground state electronic configuration, 1s2, 2s2, 2px with the electrons paired here, 2py with the electron, one electron one way, and 2pz, the electron also in the same way, right? So this specific configuration, right, is going to be uniquely associated with the term symbol. Please note it, okay? So I once again repeat, when I say that each electronic configuration could be uniquely mapped with a term symbol, only one term symbol, right? It is that I'm talking about this specific configuration. I'm not talking about the generic expression 2p4, right? Wherein I don't identify with the spins, etc. Okay, I'll give more explanation soon, but please understand this aspect first. It is that given a spin paired electronic, given an electronic configuration where we've also taken into account the spins of the electrons, right, such as this, not this one, right, then a unique term symbol can be associated with the electronic configuration. All right, okay. So, and what is this term symbol? This term symbol is, you can, one way to think about it is, a more precise representation of an electronic configuration, which takes into account all the quantum numbers in just like a couple of using only some numbers and alphabets. For example, to write this electronic configuration, you needed like, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different symbols overall, right? Of course, some of them are repeated. Okay. Likewise, over here, right? You have 1s2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So you need 19 different symbols to represent this electronic configuration. A term symbol, on the other hand, is going to be a much more precise and succinct representation of an electronic configuration. Okay. I'll tell you how to write the term symbol soon. For example, take this specific term symbol right here, this fellow right here, right? 1s2, 2s2, and then this given configuration. So, for example, you consider your 1s2, 2s2, 2px up and down, 2py up, 2pz up. Okay, right? Let's say this corresponds to m sub l equals +1. This corresponds to m sub l equals 0, and this corresponds to m sub l equals -1. So the ordering actually doesn't matter, but by convention, we're going to write that we're going to follow the maximum value of m sub l1 and go to the min value of m sub l. Okay, right? That is by convention. If you change the convention, you can still get the term symbol, but then you'll have to follow a different algorithm than what I'm going to be suggesting to you. Okay. For this particular electronic configuration, let us see how we come up with a more precise and succinct representation of the electronic configuration. All right. Now, we're going to define 3 quantities. The net. So this is what this corresponds to the spin quantum number, which can be +½ or -½, right? So S is going to be the total spin quantum number. And then my capital L is going to be the total, let's say, magnetic quantum number, and my J is going to be taking into account the coupling between spin and orbital part. So don't worry if you're not clear about what these things mean yet, okay? And my term symbol for any given electronic configuration can be expressed in terms of S, L, and J, and more precisely as it is given as 2SLJ. Now, I've just introduced 3 terms to you now. Something called as S, which is the total spin quantum number. Something called as capital L, which is the total magnetic quantum number, right? We can also call it the total angular momentum quantum number, right? I'm being informal. Informally, I'm calling it the total value of the magnetic quantum number. More precisely, it corresponds to the angular momentum contribution. Okay, right? So this is going to be coming from the quantum number small s. This is capital S. This is capital S. This is small s. So this is going to be coming from the magnetic quantum numbers, and this is going to be coming from both capital S and capital L. I will tell you how this is coming very soon. Okay, just hang on. So the term symbol is represented as 2s plus 1. 2s plus 1 to capital S plus 1 Lj, where we know this 2s plus 1 is what is called as the spin multiplicity. Okay, fine. Okay, let us see how this is going to work out for this given configuration of oxygen atom. Okay, all right. To get the total spin is nothing but the sum of all the individual spins. Now, as long as all the electrons are paired, for example, your 1s2 electrons are paired, your 2s2 electrons are also paired, and 2px electrons are also paired, right? The net contribution to your spin is going to be 0. You're just going to count the contribution of the spin quantum numbers from the 2py and 2pz, which are the unpaired electrons. So this is going to be, conventionally, this is going to be +½ plus half here, which is going to be 1, correct? So therefore, now see, you may ask me, what by convention I write it this way, but what if I write the spins the other way about, right? That is also okay. In that case, you're just going to take the modulus of this s, okay? So my s is always, the net s is always going to be a positive number, okay? Please note it. So my s here is going to be plus 1. So therefore, my 2s plus 1 is going to be 3. So for this configuration of oxygen, right, my 2s plus 1 value is going to be 3, right? Let us now look into the capital L value. I will just retain this oxygen, the representation. So where are we? I'm trying to illustrate how to get a term symbol with the example of the oxygen atom, correct? And I told you that the term symbols can be represented in terms of 3 quantum numbers, capital S, capital A, and capital J, right? Wherein the S and L quantum numbers are going to be the net contribution from spin and the magnetic quantum number or the angular momentum part of the quantum numbers. J will come to here, okay? And we already computed the S value for oxygen atom for this specific configuration to be plus 1, right? Okay, so the 2s plus 1 is going to be 3. Now let's calculate L value, capital L value. The capital L value is obtained by counting all the M sub L values, okay, right? Now, for example, for this specific electronic configuration, the M sub L for these both electrons, right? So for this given electronic configuration of oxygen atom, the L value is going to be, for this specific electron, it is going to be plus 1, correct? Similarly, for this electron also it is plus 1, right? This is from 2px. Note that even though the spin pairing is different, as far as M sub L value is concerned, it is still only plus 1, okay, right? So this is going to be plus 1 and plus 1. And what about the 2py atom? The 2py electron, it is going to be 0. And you can also calculate the one for 2pz, right? This is going to be what? Minus 1. So this is going to be 2pz, right? Now note this point. I did not take into account the contribution from the 1s2, 2s2 at all. Can you guess why? Because they're going to be overall 0, right? You understand? See, the M sub L value for this is going to be 0. The M sub L of this is also going to be 0. Correct? Are we understanding, right? Because the magnetic quantum number, right, is going to be much more important only for the p orbitals. This is how the idea of quantum numbers pan out, right? Okay. So that's why I need not take into account the 1s2, 2s2, the filled electronic configurations at all. So now that I have this, right, the total L value is therefore going to be, I mean, these cancel out, it's just going to be plus 1. Now, I'll continue here, okay. So the capital L value of O atom for this electronic configuration is noted to be plus 1. Now, just like, see, how do we assign the SPDF orbitals? We assign the small f for orbitals, SPDF. They correspond to L equal to 0, L equal to 1, L equal to 2, and L equal to 3, right? Likewise, these are going to be expressed in capital letters. My L equal to 0 corresponds to what is called as a capital S, and L equals 1 corresponds to a capital P, L equals 2 corresponds to a capital D. By the way, I mean, this just keeps going on, but for our purpose, we just stop with this, okay, right? So therefore, my capital is equal to plus 1 here. So therefore, this corresponds to what L state? This corresponds to the state of a P, a capital P, right? So in the term symbol for oxygen, the 2s plus 1 was found out to be 3. My capital L was found out to be P, right? And my J, right, finally, so my J is going to be L plus S, right? Which is therefore going to be 1 plus 1, which is going to be 2. So overall, my term symbol, I'm going to use TS for term symbol for the oxygen atom is going to be 3p2. Well, this 3 is what is called as triplet to indicate spin multiplicity. If S happens to be 1, you have what is called as a singlet. If S happens to be, if 2S plus 1 happens to be 1, you have what is called as a singlet state. If 2S plus 1 happens to be 2, right, then we call it a doublet state. And for 2S plus 1 equals 3, we call it a triplet state. So this is going to be a triplet P2 state, all right? So the term symbol corresponding to this particular electronic configuration is a triplet P2. Are we clear? So this is how, given any electronic configuration, we can uniquely define a term symbol. Okay. Now the electronic configuration should be written carefully and more precisely. It should be written in this form, and it should simply not be written 1s2, 2s2, 2p, 2p something, right? We must take into account the spin pairing and also the multiplicity of each of the orbitals, etc., etc. Only after that can we say that each electronic configuration could be uniquely mapped with a term symbol. Are we clear? Okay, right? So this electronic configuration has a very precise and succinct term symbol representation called as triplet P2. Okay, why do we care about all this? Because we are concerning ourselves with selection rules. Selection rules in what context? Selection rules in the context of electronic transitions. So why do we worry about electronic transitions? Well, because sometimes, when we were considering the different types of motions an atoms or molecules can undergo, right? In particular, when we discuss about atoms, we saw that atoms cannot undergo, translational motion, yes, but that's not of use because the energy involved, the magnitude of the energies involved are very small. So they can only undergo like electronic transitions, right? Because rotations and vibrations are ruled out. And as part of electronic transitions in atoms, what happens? It's the electrons which move about, right? Which move about from a ground state to an excited state, etc., etc. So if this is going to be the ground state electronic configuration for oxygen, and therefore this is the ground state term symbol. GS meaning ground state and TS meaning term symbol. So the ground state term symbol for O is given as triplet P2. But let's say this gets excited. Okay, let's say that the oxygen atom, right, gets excited to go to, so let's say oxygen gets excited, say by shining some UV light. And the electronic configuration changes as, and so let's say that the electronic configuration changes as from this one to 1s2, 2s2, right? And let's say that it becomes 2px2, 2py2, and 2pz0. In other words, this is m7 equals +1, 0, and -1. Okay. So let us say that the electronic configuration simply changes in the following way. All right. So I think this is an apt time to stop this lecture. Where are we? We are discussing the term symbols as a succinct representation of an electronic configuration. Why do we care about the term symbols? Because the term symbols shall be used to understand specific selection rules for electronic transitions in atoms. Okay. And why do we care about that? Because these selection rules are going to be helpful in understanding the intensities of spectral lines, which is intimately connected with detecting molecules in space. Okay. So at this juncture, where I've just introduced to you one possible excited electronic state of oxygen atom, right? And how the electronic configuration changes. I stop right here and I shall begin from this point in the next lecture. Thank you so much.